Section 7.8 is geometric sequences. I can write and use recursive formulas for geometric sequences. Big ideas here. A geometric sequence has an initial value and a subsequent sequence of values based on a common ratio. A geometric sequence can be modeled with an exponential function. The take note on page 467, a geometric sequence with a starting value a and a common ratio r is a sequence of the form a, and then we multiply by the common ratio and get ar, and then we multiply by our common ratio and get ar squared, and we multiply again to get ar cubed, and so on and so forth. A recursive definition for the sequence has two parts. Just like we talked about with recursive formulas for arithmetic sequences, same idea here. Recursive means we're going to repeat and have two rows. So with recursive formula, we have to repeatedly multiply by our common ratio. So we take the number before it, multiply by our ratio. So with our recursive formula, we have to have two rows. We have to say, where do we start? Give our initial value. And then we say the amount of the nth term equals the amount of the term before it. Remember, n minus 1 just means the term before, the number before it, times our common ratio. In an explicit definition, it's a single formula. In explicit formula, we have exactly one formula that gives us the exact answer right away. So here, the amount of any term is the value of our first term times our common ratio, and since we're multiplying every time, and as we see here, as we keep multiplying, we express repeated multiplication with exponents. And here it's going to be n minus 1 because it's our term number minus 1. If we look up here, our initial term, our first term, didn't have any r values. It wasn't until our second term, our third term, and our fourth term where we had those values. So here we have to subtract 1 to account for that initial start. But just like with arithmetic sequences, our geometric sequences that represent repeated multiplication, recursive formula and the explicit formula are very similar. In example 1 here, we're going to identify geometric sequences. Which of the following are geometric sequences? So we're going to try and figure out what are changes from one point to the other. So we have two options. To go from 20 to 200, I can either subtract and get 180, which means I can add 180, or I can take 200 and divide it by 20, and I get 10, which means I can multiply by 10. So my options to go from 200 to 220 are to either add 180 or multiply by 10. Now we're going to do the same thing between our next two numbers. But here we already have a starting part. We're either going to try and add 180, which doesn't get us to 2,000. So that is not our pattern. But if I try multiplying by 10, that does get me to the value. So I'm going to keep this pattern and see if it works all the way through. Multiply by 10. Yep. Multiply by 10. Yep. So here I have the same thing being multiplied every time. So my pattern is that we're going to multiply by 10, which means 10 is my r value. Since I have a common ratio, this is geometric. So, yes, it's geometric. And that's because I'm multiplying by the same value every time. If we check B here, I can either take 4 divided by 2 to get 2, which means I multiply by 2 every time. Or I can take 4 minus 2, which also happens to be 2, but I got there by adding. Now let's check both of them again. If I take 4 times 2, do I get to 6? No. So the multiplication isn't going to work. Now let's try the adding. 4 plus 2 gets me to 6. So I think this is going to be my pattern, but let's just keep double checking. Add 2 gets me to 8. Add 2 gets me to 10. So yeah, my pattern here is I'm going to add 2 every time, which means that 2 is my common difference. So is this geometric? No. It is an arithmetic sequence, which isn't super important right now, but we have done arithmetic sequences before. So here we have an arithmetic sequence because we're adding the same every time. But we only have geometric if we're multiplying. So in C, to go from 5 to -5, I can take -5 divided by 5. I multiply by -1. Or I can take -5 minus 5, and I can subtract 10. Now, we check our next ones. To go from -5 to 5, okay, 5 divided by -5, -1. So I can multiply by -1, but if I try and go 5 minus -5, I get a positive 10. So subtracting 10 doesn't work. Now let's double check. If I multiply by -1 again, yep. Multiply by -1 again, yep. So here, my pattern is to multiply by -1, which makes -1 my common ratio. And it's a ratio, guys, because we find it by dividing any two consecutive numbers. So when we set things up as division, we're setting up a ratio. So our common ratio here is -1. When we have a common ratio, when every time we're multiplying by the same value, it is geometric. So this one is yes. Feel free to pause here and give these a try if you'd like. In A, to go from 3 to 6, I can either add 3 or I can multiply by 2. And some of these patterns we can see, so we don't actually have to set up the ratios, but if you're not sure, guys, we can keep setting them up like we did on top. Now, to go from 6 to 12, I can't add 3, but I can multiply by 2. So let's check our multiplying by 2 again. Yep. Times 2 again. Yep. So here, I'm going to multiply by 2, which means 2 is my common ratio, and yes, this is geometric. In B, so again, from 3 to 6, we said we can either add 3 or multiply by 2. Now, if I try and add 3, do I get to 9? Yep, let's try multiplying by 2. Nope. So multiplying doesn't work. If I add 3, it does get me to 12. Perfect. If I add 3 again, yes to 15. So here my pattern is to add 3. And since I'm adding, that's going to be my common difference, which means this is not geometric, but it is an arithmetic sequence. Okay, and we talked about those, I think it was in chapter 4. And C here, these are supposed to be fractions here, guys, don't get confused by that. So to check our difference every time, to go from 1 to 1 to 1 to 1 every time, we're multiplying by 1. Over, from 3 to 9 is times 3. 9 to 27 times 3. Here, times 3. So every time I'm multiplying by 1/3. Times 1 over 3, yep. Times 1 over 3, yep. Times 1 over 3, yep. So since I'm multiplying by 1/3 is my pattern, and multiplication means we're going to have a ratio. Since I have a common ratio, yes, this is geometric. In D here, I can add 3. I'm not going to multiply there. I can multiply by 7 over 4, which isn't super helpful because it's not going to work to get to 11. I can add 4. I can add 5. I can add 6. So here my pattern's not as easily definable. It's not just multiplying by the same thing or adding by the same thing. So even though there is a pattern and this is a sequence, it's not going to be an arithmetic or a geometric sequence. So this is going to be not geometric or arithmetic, which apparently I can't spell extra there. And that's okay. Sometimes we can have sequences and patterns that aren't geometric or arithmetic. We can see here that every time we're just adding an extra one, but that doesn't fit into one of our patterns or into our equations that we've used so far to come up with equations for sequences. In example 2, we're going to be finding recursive and explicit formulas for this sequence. So here, I need to figure out what my pattern is, so I know if I have a geometric or an arithmetic sequence. So here, to go from 7 to 21, I can either add 14 or multiply by 3. If I check here, adding doesn't work, but multiplying by 3 does give me 63, and multiplying by 3 does give me 189. So here my pattern is to multiply by 3, which means 3 is my common ratio. So I have a geometric sequence. Since I have a geometric sequence, I can use my formulas. For recursive, I take my first value and plug it in, and then I have to have a second row that has what I do from there. In recursive, we repeatedly perform our operation. So here I take the value before it, the amount of the n minus 1 term. Again, n minus 1 means the number before, so the amount of the term before. And since I'm multiplying by 3 as my pattern, I'm going to multiply by my r value here. So when I plug these into my formula, this is my first value, and this is my common ratio. For explicit, we have exactly one equation that lets us find the exact value we're looking for. So here, my formula is a sub n equals my first term times my common ratio raised to the n minus 1 power. Because again, we only multiply by that common ratio one less time than the term we're looking for, because that first term is just where we start. So again, here I put my first term and then my common ratio. In this example, my common ratio is 3. So that's what I'm going to plug in here and here. And my first term is 7. So that goes here and here. So I have a sub 1, or my very first term, is 7. And the amount of any term is the amount of the term before it, n minus 1, times my common ratio, 3. This is my recursive formula. For my explicit formula, a sub n, so the amount of any term, is my first term, 7, times my common ratio raised to the n minus 1 power. And this right here is my explicit formula. So when we fill these into our formulas, guys, the very first number we plug in is our first term, and the second number we plug in is our common ratio. Now, we're going to find the recursive and explicit formula for each of the following. So I'm going to have a recursive and explicit. Remember, with recursive, we have to have our first value, and the amount of any term is the term before it times our common ratio. That did not work. The amount of the term before it times our common ratio. Our explicit formula is the amount of any term is our first term times our common ratio to the n minus 1 power. So here, to go from 2 to 4, we're going to multiply by 2. 4 to 8, we multiply by 2. And 8 to 16, we multiply by 2. And my first term is 2. So my framework looks like this for my recursive. And for my explicit, that's my framework. Now we just plug in our values. So my first term is 2. And my common ratio here is also 2. For my second one down here, to go from 40 to 20, I multiply by a half each time. So my common ratio is a half, and my first term is 40. I set up my framework, and fill in my values. First term, common ratio.